So let's get back. So here, a better way to actually do, and the correct way to actually do centralized, to some extent, learning in the example that you already seen is actually leaning more towards centralized training than centralized execution. First of all, let's do what we did for independent and fully centralized learning. So try to understand what the approach is about. So the main, let's say, intuition about centralized training and decentralized execution, all approaches that can fall under this term, is doing something that, in truth, for us, at least in this course, is what should be the best practice. Separating training and testing. This thing that, at least for us, may seem quite natural, because in supervised learning, I actually spent a lot of time in motivating why splitting training and testing, and even further splitting training in training and validation is a good idea. If you notice, up to now in reinforcement learning we never mentioned the distinction, and the reason was simply that in reinforcement learning there is not really a data set that you can split in advance. Okay, we already discussed about this. There is not really a data set that you are handed in advance, and then you can pre-process, you can split, you can do whatever you want. Because in reinforcement learning we said that the learning process is online, in the sense that the agent is generating its own learning data. Okay? While learning progresses with the same policy under learning or another policy, the distinction between on and off policy learning. So in reinforcement learning, actually, this distinction was not really something that was taken into account until later on in reinforcement learning research. Basically, sooner or later, someone realized that reinforcement learning has, and this still is an open issue that nurtures many research efforts, reinforcement learning has a somewhat intrinsic problem of generalization. We are training a policy that strictly depends on the environment for many reasons. The observations come from the environment, so part of the data that the policy is learned on is actually tailored to one specific environment, task, scenario, decision process, whatever you want to call it. The actions must have some meaning in that specific environment. Maybe they don't have meaning in another environment. The reward and so on and so forth. More or less everything in a reinforcement learning problem configuration setting is tailored to a specific environment. How can we take an agent that has been trained in an environment to perform in another one? Slightly different, notably different. Maybe we are still in the domain of warehouse management, but the warehouse layout changed, the shelves changed, the specific goals changed. Can we train a reinforcement learning agent or a set of reinforcement learning agents in a generalizable way? That's still quite a big issue. And this train and test split has been made with a number of motivations, and one is exactly generalizability. We should take some time ago, somebody said, in reinforcement learning, we too should take the habit of training in a given environment, but testing the performance in another environment. Okay, that wouldn't be probably a completely different environment, but at least not the exact same environment in which the training happened. So when in reinforcement learning, it was realized that this split is meaningful, then people started thinking that this split could actually be useful also in practice to improve learning. The core motivation is here at the bottom of the slide. Even if reinforcement learning is conceptually an online learning paradigm, okay, you learn while you are behaving. For a given number, the majority, I would say, of practical applications, you don't directly train your model in the actual environment. You usually train in a simulated version of it, in a test version of it, in a somehow protected sandbox version of the actual environment. Okay, this is not really different from traditional machine learning, in which you first train a model, validate a model, and after you are sure about the performance, you maybe integrate the prediction model in an application in your company. Okay, this is not really different, or even different from traditional software development. You develop software in a sandbox environment, you test it with selected users, whatever, and then you release the software when it's ready in the production environment. So we should do the same. But when we are doing simulations, actually, many of the domain constraints that we may have in the real world are not really there. Actually, because a simulation is a simulation, so it is not the completely truthful representation of the reality, but it is only a model of the reality that obviously should capture, okay, should model the relevant aspects, but can also make some simplifying assumption. For instance, one of the domain constraints that we mentioned is the lack of communication. Okay, we may have that in our scenario, communication is costly. Well, communication may be costly in the real world, but if you are simulating our scenario with a computer, communication is not costly. The simulator runs on a single server. We don't really need to communicate anything. Okay, communication is fake. Okay, so since training usually is done in a simulated environment, in a virtual environment, okay, we can make some assumption. For instance, here it is not about communication, but it's about, hence we can assume that somebody has access to the whole environment state. Maybe not the agent, but at least somebody, the simulator itself, has access to the full, complete state. So, the way in which all of the centralized training, the centralized execution approaches, and there are different ways to actually put this paradigm into practice, is basically doing this. In training, since we are doing training most often in simulation, we train a single policy. We try to exploit as much as possible full observability, communication between agents. We try to exploit every single piece of information we have as if, okay, as if agent could observe everything. This has the potential of improving learning, okay? Better observations, agents can communicate about the intended actions, they can exchange rewards, they can exchange the parameters they are learning, so for instance the state value functions or the state action value functions, this kind of stuff. Cool. Problem is, we must also find a way to make this policy that we are learning up to now in a more centralized than decentralized way exploitable after training, so in the real world after deployment. when maybe all of this communication, full observability, all of these simplifying assumptions do not hold anymore. Okay? So the basic idea is that in centralized train, decentralized execution, we train a single policy that controls every agent, but the policy is parameterized to each agent, which means the policy can distinguish, you are agent 1, you are agent 2, you are agent 3. You are the agent that gave me that observation, you instead gave me that other observation. So the policy has a parameter which is, for instance, the agent ID. Okay, this is just an example, but the core point is that the policy should have a way to distinguish between agents. That's why we said it needs to be parameterized to each agent. So for instance, the input is no longer, as in the naive centralized case, is no longer a concatenation of all the observations. Because in that way, we would lose information about who actually made that observation. So this time it could be, for instance, a collection of agent observation pairs, so that we keep the relationship represented. The output this time is not a joint action, okay? Or better, it is still a joint action, but this joint action is the concatenation of every action, of all the actions of every single agent, that is, however, conditioned by the observation of the agent. What does that mean? It means that instead of telling an agent, look, do this, no matter what, because I, the learned policy, the learning entity, I am telling you to do so, what I learn is do an action depending on your current observation. Okay, so I have an estimate of state values and state action values, but in considering which action to pick, consider your current observation at this time step. Okay. So learning, training happens in this way. During deployment, okay, we deploy the policy on each agent, which means basically that essentially we copy the policy. Okay. The learned policy gets copied, replicated to each agent. So we don't need to communicate to this central entity anymore. And we know that everything will work. Why? Because we didn't tie the action of an agent to the whole observation, to the concatenation of all the observations. We tied the action of an agent to its own observation. Okay? That's why it works. Even here, the input of the policy will simply be one pair, the current agent and its observations, and the other pair will be empty. Okay, I don't know what other agents are seeing. But the policy can still dictate what this agent should do, because at least it can condition the policy based on that agent observation. So this is the caveat, okay? The technical way we achieve this separation between training and testing, so learning and deploying a learned policy, where in learning we may have some simplifying assumptions to speed up learning, and we are not obviously guaranteed that the deployed policy will be as effective as the policy was in learning, but at least we are guaranteed that it will not break in stupid ways like the one we just experienced with the fully centralized case. So let's try to depict a bit maybe more intuitively what's happening. Training is similar to the centralized training. There is a centralized controller, the algorithm runs gathering observations from all the agents, and trains a unique policy. But this time, the output is not simply a joint action. It is a set of actions that are conditioned on the agent identity, okay, for instance, or on the agent observation. We could condition on many different things. Agent identity is simply the most easy to understand. But we can even decide to condition on the observation. I don't care who is the agent. I care what the specific observation is, which means in which state is the agent. Don't forget that the observation is simply the perception that the agent has on its own state. So that's actually what I want to conceptually condition on. In testing, when the policy is learned, so when I, for instance, do not want to learn anymore, I freeze the policy because in my simulation, in my experiments, the policy was really good. At deployment, the learned policy is simply copied, okay? It's replicated, it's copied. Then each agent feeds the policy with its own observation, as it was in independent, and gets its own action. That's it. I don't care if when I feed the policy with these pairs of agent observation, most of these pairs will be in some sense empty because I don't know the other agents what are doing in deployment. We don't communicate anymore. I don't care simply because the policy don't care as well. The policy doesn't care because the only thing that the policy needs to work is one observation to condition the action. Okay, that's it. So this is what happens actually. So for instance, in practice, let's try to see what happens. And again, this code is a bit convoluted if you look into it. That's why I highlighted the, but at the same time is also easy to detect where to change something. If you compare this with the code excerpt before, it is the exact same code. We only changed some Boolean values, okay? We only changed some configuration. This time, agents do share parameters. In training, they can. So they, for instance, can share the state value functions they are learning. Fine. Okay. This can improve learning because many agents are deployed in different parts of the environment. So if they can share their state action value functions, they can explore better the environment. I don't need every single agent to go everywhere. I just need that all the agents all together go everywhere. And this was as before. Before I think we always have true. Now, the fundamental part is that we don't want to share the observations. Okay? We don't want that. Each agent should be, the policy should be able to distinguish, okay, which observation is coming by who, from who. Why? Because this will be the case in deployment. Simply because of that. In deployment, we said agents should no longer rely on each other to understand what's going on. Then we can still evaluate centrally the expected return. In training, we want to evaluate the expected return in training, not once the policy is already learned and frozen. We don't care about evaluating the expected return there. So in training, we can evaluate the expected return in a centralized way, which means, okay, if this agent do that and that agent does that, this agent gets this reward, this agent gets this reward. We can do this in training, okay, in a centralized way. And actually, this very simple change, okay, so not sharing observations, Where was the? Should be here the example. No. Where? Maybe it's not in the slides. Yeah, you have the example code that in the repository. Anyway, so with this simple change, apparently simple change, but it took me a lot of time to find some code that will keep this change localized. We get to this situation. Same environment, obviously. Random policy at the very start of learning. We now see a more reasonable learning curve. And in fact, the actual behavior, final behavior, is this one. That more or less, for what we can see without knowing whether it is independent learning, centralized training, decentralized execution, this is more similar to the one we had with the independent learning. At least that they are doing something meaningful. Okay, they are not moving in team, in flocks as before, without achieving their goal. They can avoid obstacles. The green and the blue one avoided a collision. They can reach their own goal. Even here, the orange, the blue and the green try to avoid each other. So just looking at the end result of training, we wouldn't be able to tell whether this was independent learning or centralized training, decentralized execution. Okay. This time, the policy that the two learning modes converge to is very similar, at least for a human being. Okay, for the human eye, it's very similar. It's a reasonable policy. It achieves the goal. It seems more or less an optimal policy. Okay. And again, the only thing that changes, that is not really visible in code, but I did it on purpose, otherwise it will get even more complicated, is that the policy that we are learning is conditioned on the observation of the agent, so can distinguish between agents. This means that the policy, in a sense, it is still a big policy, like in the centralized case. There is still somewhat the problem of the joint action space, of deciding an action for every agent. But this time, the portion of the policy that we need in deployment to actually work is a smaller portion. Okay? We only needed to activate, let's say, the portion of the policy that corresponds to a given observation. So that's why we actually can have different behaviors. Keep in mind that one thing to notice that may appear weird is that the policy is the same. Okay? All of the agents has the same policy. Think about the same decision tree, the same if-then-else sequence. So how can they make different actions? Because at each time step, I could argue probably that at each time step, each agent is doing a different action. The green agent is doing north, the orange and the blue are going right. Well, that's why. They have the same policy, the same decision tree, the same if-then-else. But they evaluate the policy differently, depending on their observation, depending on their context, the state in which they're in. That's why it's possible to have one policy that actually has different behaviors. Yes?
Does this reduce the computational cost as compared to the independent one?
I won't say that it reduces the computational cost. For instance, because in general, I don't think it's easy to answer. In general, probably could be argued that the computational cost increases. Because, for instance, in independent learning, one thing that comes to mind, I could easily parallelize learning. Every agent is per se. Just use multiple CPUs, multiple processing nodes for that. Here instead, I still need to do it centralized. But the thing is that, on the other hand, in this way, probably information is used better, because the same information can be used by aggregating different information from different agents. So in general, it is not easy to answer, but probably learning is much more efficient in this way, where usually in reinforcement learning, efficiency and also efficiency, also efficacy, which are two different things, no? Efficacy is how good is your solution. Efficiency is how costly is achieving the solution. You don't usually measure efficiency in wall clock time, okay? So my training took 3 days. You usually measure sample efficiency. How many samples, how many state action reward samples did my algorithm need to converge? So probably this version is much more sample efficient. And the reason why is something that even if we don't know actually the details, we can grasp. The fact that in training agents are contributing to a single policy means that in this run, let's assume we are not in deployment but in learning, so it's a learning run. The green agent is exploring this portion of the world and probably will end up exploring this portion. The orange agent will end up exploring this portion. So two quite different portions, no? Almost no overlap. All of this exploration fits the same policy. So we are using our samples more efficiently. If we were in independent learning, this policy will know nothing about this portion of the world, and this policy will know nothing about this portion of the world. Actually, a precise answer to this question would also need to account for the specific algorithm, whether we are using neural network or not, or which kind of neural network and stuff like that. So again, you can play with these examples if you want. Now there is, I think, if I remember correctly, a quite short digression in deep reinforcement learning or multi-agent reinforcement learning. Here I put the multi-agent stuff in parentheses, simply because the things that we are saying here are applicable to both reinforcement learning in this single agent and multi-agent case. We don't care. And some of the things probably we already mentioned. Obviously nowadays the so-called tabular algorithms, so the algorithms that explicitly keep track of the state action or state value function, like Qtable, SARSA, all of the temporal difference families, are more or less obsolete. In some cases they may be fine. They have some properties that make them still desirable in some cases, but performance-wise they are more or less obsolete. Okay, because deep learning took over, so neural networks took over. We have GPUs. We have also the brute force to train these kind of approaches that, for instance, in 1980 wasn't even possible to imagine. So why? What is deep reinforcement learning about? Again, I will refer to reinforcement learning, but this is applicable to multi-agent reinforcement learning as well. One core problem of the approaches to reinforcement learning we have seen so far, and we didn't see many, but let's take as a reference Q-learning. So keeping an explicit track of the state action value function, for instance. No, that's what Q-learning does. If you remember the toy example with the frozen lake game, the table in the middle with the colored arrows the colored tiles and the arrows, I told you that basically that was the Q table. That was the state action value function, explicitly represented. Okay? That thing, in the vast majority of practical problems, grows hugely at the point of becoming computationally intractable. That's the main problem. So, the main problem of this kind of traditional reinforcement learning algorithm is representation of value functions, state and state action value functions, even of policies, okay? Because if you think carefully, having that kind of table is actually having the policy. That's the policy. For each tile, give me your highest number for the next action. That's the policy, actually. Okay. So, representing all this sort of stuff explicitly with a graph, with a table, with a dictionary, with a map, with whatever data structure you can imagine, quickly become infeasible for real-world problems. So, this issue of representation mainly unfolds along two dimensions, okay? One is scale and one is sample efficiency. Scale means what we just said. An exact representation of this sort of things grows linearly with the input. One cell, you have a big table with one cell for each state action pair. That's it. If you try to, our experiment with the Frozen Lake game, we did 3 rounds of training with if I remember well, 2,500 episodes each. So less than 10,000 episodes, no? Altogether, 7,500 episodes. It took 2 minutes, I don't remember correctly, but a few minutes. That was a 7x7, I think, grid. Just take it to 100-100 grid and see how time increases and how it could be that actually learning crashes because your computer goes out of memory. Because you need 100 by 100 cells, and each cell will have 4, 5 actions, possible actions in it. So this is the first problem. Actually, building and maintaining this representation may become unfeasible. A parameterized representation does not. What does it mean, a parameterized representation? An approximated representation, okay? We chose to approximate this kind of things, which are functions. The policy is a function. As input takes observation, and that's it, basically. And as output gives you an action. That's a policy, is a function. And the value functions, which are functions as we know them, we can approximate them. Okay? In whatever way we want. And then we solve the problem of scale. If I decide for an approximation of my value function, which is, I don't know, some linear combination of whatever, with a fixed number of parameters, I don't care how my observation space grows. I have the same number of fixed parameters. The other dimension is that of sample efficiency. This is perhaps more subtle to grasp. When we update our value estimates, again, state action or state value, we don't care. When we update the Q value, no? Remember the slide with the QS, A, left arrow, and how to update the Q values. Okay, when we do that update, we can only do the update based on the explicit individual single state that we just experienced. I was in a tile, I moved, I ended up in another tile. Can I say something about the nearby tiles? No. I can only say something, I can only update the Q values of this type, no matter how close the other states are. I can only update one state, the one I experienced, no matter if they are similar. Okay? I may have a number of states actually that are very, very similar in their representation. Okay, similar coordinates, similar properties, I don't know, but very similar features. So much that, well, maybe the fact that I ended up in that tile is more or less the same as I would end up in the adjacent tile. But I can't, okay, express this. With a parameterized representation instead, exactly because in a sense we are doing something that is similar to dimensionality reduction that we have seen in a previous lecture. By the very fact that we are approximating our state action value functions as state value functions, I cannot even tell whether I am in this style or in this style. I'm approximating. So obviously this is bad in the sense that I'm losing information. But it's good in the sense that wherever I end up, in whatever state, okay, given a certain radius, if you wish, okay, I can update with one sample all of the similar states. That's what happened. Imagine that this sort of parameterization is a sort of discretization. You have a continuous variable and you discretize. Okay, so you have bins. On the one hand, you lose information. Okay, if I have one bin that goes from 0 to 10, whether the actual value was 9 or 8, I lose that information. I cannot tell anymore. At the same time, I gain something. Okay, I gain the fact that whatever value of the variable between 0 and 10, I can update all of that bin. Okay, so I gain something also. That's the same here. Okay, let's assume that I convinced you that representing the functions involved in reinforcement learning with some parameterized, okay, approximation is useful. Now the question is, what parameterized approximation? No, there may be many. Okay, it's similar to the question of what prediction model do we use? Supervector machine, linear models, decision trees, whatever, it depends. Well, in this case, if we happen to have a parametric function that can generalize, that can be used to learn any kind of function, that would be nice. Okay, we don't have to decide in advance. So let's assume that somebody, a mathematician, a statistician, we don't care, gives us a generalizable representation. So a parametric function with parameters that we call theta. That's simply what does it do? What we said so far. Tries to approximate the true function. If all of this kind of stuff remembers you about building predictors model, it's fine. It's actually similar. Okay, it's very similar. This could be a function that predicts a dependent variable based on independent variable. Okay. So we want to learn a parametric function. We don't want to explicitly represent our Q values. We want to learn a function that enables us to estimate these Q values. So the learning goal is finding the theta that push our approximation as close as possible to the ground truth. How can we do this? Well, probably we already mentioned this. But we minimize a loss function, which measures somehow the error. How distant it is the ground truth, the true value from our estimate. Let's try to minimize this distance. Let's find the parameters for our function that minimize this loss, this error. Nice. It seems we are back to our comfortable supervised machine learning environment. With optimal parameters, our estimate for states that we never saw before, so for testing data instead of training and validation data, could be arbitrarily close to the true value. Ideally, could be 100% accuracy, okay, 100% precision. Well, turns out that the best generalizable representation that we have is based on neural networks. They are universal function approximator. There is also this sort of theory that explains why even one only hidden layer can approximate any function. Okay, so it makes sense that we don't really spend too much time in deciding which kind of parametric function we do want, but just go for some configuration of a neural network. Also for other reasons, not only because neural networks can, and deep neural networks with more hidden layers can approximate any kind of function, but also because they can also learn which features do matter. Ideally, again, there are lots of technicality here, but that we won't see, but ideally, if we throw a random dataset to a neural network, if some of the columns, some of the features in the dataset don't really matter, the neural network will simply learn to ignore them. So that's another added benefit. And another is that, differently for many other parameterized functions, they deal well with nonlinearities. Okay? They don't care if something is nonlinear. If the relationship that links the input with the output is nonlinear, the neural network will simply learn a nonlinear mapping. Fine. So, to some extent, they seem a panacea to all the problems. Okay, a solution that fits all the use cases and is wonderful and whatever. Obviously, it's not always this way. What are the main kinds of neural networks? There are many kinds. Here I only mentioned 3, but we will really only focus one, which is the very basic one, the so-called feed-forward neural network or multi-layer perceptrons, okay, that we already mentioned during classification. Okay. Correct me if I'm wrong, but I think we already mentioned it, and also in regression probably. Then there are convolutional networks, which are especially good as working with spatial data. For instance, visual data, okay? Data that has some sort of spatial correlation. And then there are also recurrent networks, which are instead especially useful for time series data, for data that has not spatial patterns, but temporal patterns, okay? But we won't really go into these details. We will focus on this kind of networks, which are the basic building blocks also for these other networks, okay? So how can we train a neural network? Did we already see this slide? Yes, okay, so this is a sort of refresher, no? Let's assume to have a dataset, okay? Some independent feature. The dependent feature can we bring this to the reinforcement learning realm? Well, yes, I mean, the independent features could be the observation features, okay, the features of the observation space, and the reward that we sample. And the dependent feature could be, okay, now what action should I do? So that's easy to do this one. So, we gather an observation, we estimate our functions, we compute the loss, so what was the true value function and what is the one we predicted. We do by propagation, gradient descent, okay, all the things we already mentioned. And we adjust our weights. Problem, if you remember. This works for supervised training. With the loss, you need the ground truth. We don't have the ground truth in reinforcement learning. We don't know the estimates, the value estimates of a state. We don't know the value estimates of a state action pair. Okay? We don't know what the optimal action was in this context, in this state. We are learning it. So what we do is something that we already mentioned when we were talking about temporal difference learning. Since we don't have the ground truth, we substitute the ground truth with a target. Do you remember in SARSA what we said? Our target was the best estimate I could compute up to now. That was our update target in SARSA. In Q-learning, the update target was similar. Okay? So again, we need a target, which is here represented by this y. We don't care which target. Okay? This is something for which different learning algorithms differentiate. Okay? We don't care about this technicality. What I do care is that you know that, well, this works for supervised learning. For unsupervised learning, we need something else. We don't have the ground truth, so we need something else. Okay, we need a target, so-called update target. For example, in Q-learning, we have seen the Q-learning update rule, and the neural network-based version of Q-learning is very similar to the tabular Q-learning, okay, the explicit representation of Q-learning. What is in some way the only difference? We are not keeping track of the Q values in a table, but what keeps track of the Q values is a neural network. That's it. So, obviously we didn't go into many details, okay, about neural networks, the actual architecture, how many layers, how to choose the activation function. We did some of this discussion back when we dealt with supervised learning, and we can do the same discussion here. But what I want you to take away from this lesson is the purpose for which neural networks are put into reinforcement learning. Okay, which is approximating these functions, value function, state action function, the policy function, that will be otherwise quickly growing out of hand. That's the purpose. Okay. Neural networks bring along some benefits, being able to generalize any function, so learning which features do matter, whatever. They also bring along many problems, usually many technical problems. Okay? Here I mention a few, but there are many problems. And actually, one thing I personally don't like about neural networks applied to reinforcement learning, even if they are really achieving impressive results, is that when you bring a neural network into a reinforcement learning problem, you suddenly have to face many technical issues about how to make the neural network work best. Okay? So, for instance, do you remember the moving target problem that we mentioned in multi-agent reinforcement learning? Let's go back to multi-agent stuff. We mentioned this term when talking about non-stationarity, okay? The fact that the environment becomes non-stationary means that the policy I'm trying to learn, the goal I'm chasing, may change depending on what others are doing. So I need to adapt. The policy that I was learning a second ago may be now obsolete. Neural networks actually worsen this problem. Because the fact that we need a target to do gradient descent, to do backpropagation, okay, to compute the loss, we need a target, means that we need to invent a target. The only way we have to invent a target basically is by looking at our policy, but the policy is also the target. So this is a dog that chases tail, okay? So actually neural networks worsen the problem of the moving target problem. Another issue is that one essential assumption for application of neural network, which is having access to independently and identically distributed data, which means that the dataset that the neural network works on can be shuffled, can be arranged in several different ways, doesn't matter. In reinforcement learning does not hold anymore. Okay, in reinforcement learning, the agent is generating its own data, so it is not independently and identically distributed. It depends on what the agent is doing. So actually, one of the basic assumptions that make neural networks good is violated in multi-agent reinforcement learning. This may be seen similarly to what we said about Q-learning. So you simply lose some guarantee, but maybe they work anyway. One of the things that you may often encounter is this notion of replay buffers. The fact that data in reinforcement learning is not IID means that the neural network is likely to overfit on recent states, okay, forgetting the past. A partial solution that alleviates this issue but doesn't solve it is the replay buffer, which means do not learn once from each trajectory sample. Keep the trajectory samples that you generate while learning in some data structure, and periodically replay those samples. So fake to be in the same extra state and learn again. So this actually, for instance, increases training times a lot. Then there are other issues. One that is very intuitive is interpretability. With a Q-table, it's very easy to know and to check what's happening, as we did for the Frozen Lake example. We had those nice arrows and colored tiles. Very easy to know what the agent is doing, what is its criteria for choosing actions. With a neural network, not so much. There is a lot of work on so-called explainability of neural networks. So try to see what's going on behind the scenes, but it is not quite like having a table. And something that may seem weird, sample inefficiency. We said that we want to use deep reinforcement learning because that way we can use a sample to update other state. How could it possibly be that neural networks are sample inefficient? Well, it may be, for instance, for this reason. You need to use replay buffer, which means that each individual sample is less meaningful for the overall learning. Obviously, we only scratched the surface of deep reinforcement learning. I don't care about the specific algorithm, but this is only for single agent reinforcement learning. we basically had a very partial overview of the research landscape limited to algorithm. So, for instance, the algorithms that we mentioned, temporal difference, deep Q-learning, are all model-free algorithms, which means that are algorithms that don't care about learning the state transition function, the T function that we said knowing in reinforcement learning we usually assume not knowing. Exactly, this kind of algorithms don't care about modeling that transition function, since we assume not to know that. We only care about learning an optimal policy. So here you can have many algorithms, SARS, Q-learning, deep Q-learning. Somewhere here, PPO is proximal policy optimization, many of these algorithms, okay? But there is a whole other field of research which is model-based reinforcement learning, which means, wait. Okay, we agree that we assume not to know the state transition function. But if we could learn it, we wouldn't need to learn an optimal policy. Once I learned the state transition function, I can simply do dynamic programming. I know T. Now I don't need to estimate the state value function. I can calculate it. So there is a whole branch of research that is model-based reinforcement learning. Okay? Usually when you want to learn the model. So all this huge field is only constrained to Markov decision process. Okay, so for another kind of game, a POMDP, a decentralized POMDP, a partially observable stochastic game, whatever, probably there is another tree like this one with other algorithms and whatever. And obviously the same happens in multi-agent reinforcement learning. Okay, so here you have many different algorithms based on many different things. The slides you could simply throw away them, okay? It's just to show you that we really sampled only a bit of the surface of this kind of stuff. And it's okay this way. This is not a course about reinforcement learning alone. So let's do, yes. No pause, so we finish a bit early, since we have another lesson this afternoon for those of you who want to attend. The last slide is just a software overview. So let's say that somebody isn't scared enough to avoid reinforcement learning and wants to do something in reinforcement learning. You are welcome. And the software, the state of software is a mess, because this is a relatively new field. So it is not like doing, I don't know, industrial simulation. There's any logic and that's it. Okay? It's not like this. It's a bit more complicated. Okay? There's not a really standard de facto or normative standard to do this kind of things. There are lots of libraries that usually have been created first by big companies like OpenAI, DeepMind, Google, Meta, whatever, and then maybe are donated to the research community. Or there are libraries that are simply the effort of some independent researcher like me or whatever. So in these slides you just find an overview, some pointers, okay, some clickable links, but I would say that if you want to do something in this regard, this is the last step. Okay, so first decide which kind of problem do you want to attack, how can you define your learning process and whatever, and then at the very last, together we decide which kind of libraries to use. One specific difficulty in reinforcement learning compared to, for instance, supervised learning, in which basically, I don't know, you use scikit-learn and call it a day, is that we have, if you remember, two big ingredients in our reinforcement learning problem, the environment and the learning algorithm. Well, not all the researchers have the strength or they care about both. So as a result, you can have libraries that only give you environment, and you can have libraries that only give you algorithm. And then you need to put the two together. Sometimes it's easy, sometimes not. Okay? So, again, this is a lot of information. Just ask me if you need some stuff. And here is just some honorable mention of the libraries that are a good, in my opinion, are a good trade-off between how well known and stable they are and how easy it is to start doing something. Gymnasium, for instance, is a very easy library to start playing with single agent reinforcement learning. There are lots of ready-made environments, video games, robotics, whatever. It's very easy to set up. With 15 lines of code, you can get up the Frozen Lake example to be running. Okay, very easy. There is good documentation, tutorials. Petting Zoo is more or less the same, but for the multi-agent case. But both these libraries only give you environments. If you want a learning algorithm, either you implement itself. In our Frozen Lake example, I implemented Q-learning. Otherwise, you need to integrate those libraries, and here are an example of more complex library that I don't encourage you to use. This is a traffic environment. This is for learning soccer. This is an environment inspired to Minecraft, so a multi-agent world in which you need to craft stuff, gather resources, fight enemies, and this is based on StarCraft, which is another massively multi-agent player game. If you use those two libraries, Gymnasium or Petting Zoo, you need the algorithm. Either you implement them, Q-learning is very easy, or you need some of these libraries. For instance, table-based racetrack is the most famous library for single-agent reinforcement learning, which doesn't mean that you can't use the library for multi-agent. It means that if you do so, you are forced to the independent learning setting or the fully centralized setting. This is a library instead that also considers multi-agent systems, but the learning curve here is quite steep, so I really don't encourage you. TorchRL may be an alternative, but this is more for those of you that maybe want to get their hands dirty with neural networks. And the last slide is similar to the one with the reinforcement learning algorithms. It is just an example of the different ramifications that research in reinforcement learning can take. Okay. So you can go multi-agent, you can try to learn the reward function. This is called the inverse reinforcement learning. Somebody says, look, learning from own experience is too costly. In the real world, it will never work. What works in the real world is learning by imitating somebody that knows what it's doing. That's imitation learning. You have hierarchical reinforcement learning. Trying to understand how to win at StarCraft is too complex. Let's decompose the goal in different sub-goals. Offline reinforcement learning, doing simulation is too costly. Let's record all the trajectory data in a dataset and do what we are doing for supervised learning, basically. Learn from a dataset. That's called offline reinforcement learning. Okay. There are many research fields also at the intersection between with game theory. Okay, so that's it. As we anticipated, this basically concludes the content of the lecture. So for those of you who want to stay, this afternoon we will start doing an overview of programming in Python.